Investigating this complex rotational behavior is crucial for understanding how mass and gravity interact on a galactic scale. The spiral arms of the Milky Way are shaped by density waves gravitational disturbances that move through the galactic disk, causing material like gas and dust to compress in certain areas. These compressed regions become fertile grounds for star formation, often giving rise to bright clusters known as stellar nurseries. As stars and gas move through the galaxy, they encounter these waves, leading to patterns of accumulation and dispersion that continually reshape the structure of the spiral arms. The Milky Way contains a broad variety of stars, which contribute to its unique structure and behavior. Some areas harbor young, massive, and hot stars that burn brightly but live briefly. These stars are typically found in stellar nurseries within the spiral arms. Other regions are home to older, cooler, and longer-lived stars. These stars are more stable and often grouped in various types of clusters. Open clusters, composed of relatively young stars, loosely bound by gravity, and globular clusters, consisting of older stars densely packed in spherical arrangements, both orbit the galactic center. These stellar populations, with their differing lifespans and dynamics, play a vital role in shaping the galaxy's evolution. Among the most intriguing findings from Webb and other observatories is the detection of over-velocity stars, objects moving at extraordinary speeds, far exceeding the typical velocity of stars in our galaxy. Since their discovery in 2005, astronomers have sought to understand what could cause these stars to travel so fast. Their motion is believed to result from dramatic gravitational interactions, especially with extremely massive objects like supermassive black holes or through dynamic encounters in binary star systems. A primary suspect in these events is Sagittarius A*, the supermassive black hole at the center of the Milky Way. This black hole, with a mass millions of times that of the Sun, exerts a gravitational force strong enough to fling stars outward at high velocities. If a binary star system passes too close, the black hole may pull one star in while catapulting the other away, a phenomenon akin to a gravitational slingshot. Such rare and extreme events can eject stars at speeds that allow them to escape the Milky Way's gravitational hold. But supermassive black holes aren't the only mechanisms for producing hypervelocity stars. Events like supernovae, the explosive deaths of massive stars, can also impart enough energy to propel companion stars at tremendous speeds. In binary systems, complex gravitational interactions may be sufficient to eject one star. Dense star clusters, where stars are packed closely together, may also produce similar outcomes under specific conditions. Despite the varied origins, hypervelocity stars share some common traits. They are often exceptionally massive and luminous, traveling at minimum speeds of around 1.5 million miles per hour, well above the escape velocity of the Milky Way, which is approximately 1 million miles per hour. Previously, such stars have typically been traced back to the galactic center, reinforcing the theory of a gravitational slingshot from Sagittarius A*. However, when astronomers began to search for smaller stars, those similar to our Sun among these high-speed travelers, they found something unexpected. Using extensive data from the Sloan Digital Sky Survey, researchers identified stars with unusual motion patterns. Upon tracing their paths, they discovered that many of these stars did not originate from the galactic center, as expected. Instead, they appeared to come from random directions throughout space. Hypotheses suggesting origins in nearby galaxies like Andromeda were ruled out after further analysis. This raised new questions about the forces behind their high-speed trajectories. In parallel with these astronomical investigations, physicists studying the subatomic particle known as the muon at Fermilab in Batavia, Illinois, reported surprising results. Muons, which are similar to electrons but more massive, displayed a peculiar wobble when subjected to a magnetic field. This behavior deviated from predictions made by the standard model of particle physics, hinting at unknown particles or forces influencing their motion. The experiment revealed discrepancies between observed and expected results, suggesting that our current understanding of particle interactions may be incomplete. The experiment was conducted under extremely cold conditions, close to -450 degrees Fahrenheit, a superconducting magnetic storage ring 50 feet in diameter. Muons were accelerated to near-light speeds and sent through this ring, where their interactions with other particles produced measurable effects. These interactions changed the way the muons wobbled, suggesting new physics beyond the standard model. Such findings, if validated, may eventually help explain some of the mysterious forces at play on a cosmic scale. While the James Webb Space Telescope continues probing the universe, it has also explored distant regions within our own solar system. One such area is the Kuiper Belt, a vast zone beyond Neptune, filled with dwarf planets and icy bodies. This region, often called the graveyard of the solar system, contains ancient celestial remnants that offer clues about the early stages of planetary formation. Bodies like Pluto, Haumea, Makemake, and Eris inhabit this zone. Along with countless smaller Kuiper Belt objects, KBOs, these icy objects serve as time capsules from the solar system's infancy, preserving the original materials and conditions present billions of years ago. Scientists are especially interested in their chemical composition and internal activity, as some KBOs show geological or atmospheric changes despite the extreme cold. KBOs emit light in the infrared spectrum, which the James Webb Space Telescope is specifically designed to detect through infrared spectroscopy. JWST can analyze the chemical makeup of KBOs and detect features invisible to the human eye. Some of these distant objects exist in binary or multiple systems and may have rings or small moons. Their wide range of colors, shaped by composition, radiation exposure, and age, helps researchers categorize and study them. JWST is equipped with powerful tools for such observations. Instruments like the near-infrared camera, NRCam, the near-infrared spectrograph, NRSpec, and the mid-infrared instrument MIRI allow scientists to gather high-resolution data on the earliest galaxies, star-forming regions, exoplanets, and faint celestial bodies. The Fine Guidance Sensor FGS and Near-Infrared Imager and Slitless Spectrograph NIRIS ensure accurate alignment and enable broad-scope surveys beyond our galaxy. JWST also supports efforts to unravel the mystery of dark energy, a force believed to drive the accelerating expansion of the universe. In coordination with missions like Euclid, Webb's infrared capabilities will deepen our understanding of how dark energy operates across cosmic time and space.